mentioning then, at the origin of life, we have this component in the ultraviolet UVC range, which according to us was responsible for the dissipative structuring of the fundamental molecules. And this peak existed for about 1,000 million years. That's an awful long time before oxygenic photosynthesis produced oxygen. And after being absorbed by, for example, metals, the oxidation of these metals, the banded iron formations, after the metals were oxygenated, then the remaining oxygen then was left to form an atmosphere, and then in the upper atmosphere form ozone, which removed this light, this UVC light. So about 1,000 million years after the origin of light, this light disappeared. And then as we go through time, we find the intensity in the visible increased until we arrive at today, which is the yellow line. These dips in the spectrum are related to the absorption of water in our atmosphere. So, as I think I mentioned before, if we look at the ratio of this UVC light arriving at Earth's surface during the Archean compared to what's arriving today, we get these lines, these three lines in the black and the gray. So this work was done by Lawson et al. And it's really a simulation, assuming we have different amounts of carbon dioxide. So they assumed some reference case, which was in the middle, let's say, the deep black line. And they also assumed two other cases, one in which we increased the amount of carbon dioxide in the atmosphere by 10 times, and another in which we reduced it by 10 times, and another in which we increased it by about 5 times. So that gives these three different ratio spectrums. Now it's very interesting. If you plot the absorption spectrum of DNA, it falls very nicely on this ratio. So that is telling us that DNA is somehow optimized to absorb in this UVC range. Okay, these intensity values are not, well, these three are correct, but this is just schematic. Okay, but the shape with respect to wavelength is correct for DNA, the absorption of DNA, the blue line. So that gives us some idea that these molecules were really dissipative structure that were designed to absorb and dissipate. And not only do they absorb strongly, but they dissipate very rapidly, as we see by these graphs. Now, these graphs are just the excitation of these different base molecules. With a 260 nanometer photon, a pulse from a laser, very sharp pulse, very sharp in time. And then we look at the excited state, how quickly it decays. So we have a population from the laser pulse, and then another pulse which tries to excite it even further. But as I mentioned, that once the molecule is in the first electronic excited state, it's not going to absorb another photon, sorry. So the system starts to decay, and this is a measure of how rapidly it's decaying. And within less than a picosecond, most of the excited state has decayed, and that, of course, is decayed through this conical intersection. So we excite the molecule, it goes to the first electronic excited state, in which, in fact, the molecule is slightly deformed. And when it does deform itself, the vibrational states superimposed on that deformed molecule connect or are degenerate in energy with the vibrational states on the ground state. So the system can go very quickly from the electronic excited state to electronic ground state, emitting all of the energy, this vibration, which is eventually absorbed by the water, which is in solvent around the system. So both RNA and DNA then are very excellent and extremely rapid dissipators. That makes them very resistant, of course, to ultraviolet light. And that is the reason given by the biologists today for this very curious or very amazing attribute of these molecules to absorb and dissipate so rapidly. But as I mentioned before, there are much easier ways to make the molecule resistant to this ultraviolet light, for example, by being transparent or by reflecting the light. So to have this conical intersection is not so easy. You have to be specially designed to have this conical intersection. So in fact, we believe that these molecules were designed for absorbing and dissipating by nature. And if you really look at all irreversible processes and all structuring which is occurring because of irreversible processes, you will see that these structures are designed by nature to dissipate the gradient of the generalized chemical potential over the system. In this case, it is a gradient of photons, okay? This is a different spectrum, which is incident, and a different spectrum, which is emitted. So that gives us like a gradient or a generalized chemical potential, which we call the photonic potential. But there are also other dissipative structures which can form with other gradients over the system. For example, a gradient of chemical potential can give rise to the structuring in the Belousov-Zhabotinsky reactor system. And we can also see there that those designs or those structures which occur through the Belousov-Zhabotinsky reactor system are designed to dissipate chemical potential over the system. Or another case is that we have a temperature gradient, and then we have the formation of convection cells. And again, these convection cells are designed by nature to dissipate the temperature gradient over the system, because when they form, they increase the dissipation of the system. So it's more realistic to imagine that these molecules were designed by nature to absorb and dissipate this UVC light. For example, we know that there are tautomers. For example, if you move a hydrogen atom from one position to another on one of the bases, then you destroy this rapid dissipation. You don't have a conical intersection anymore. So the non-natural tautomers of the bases, which you can make very easily in a laboratory, just as easily as you can make these bases in a laboratory. These non-natural tautomers have much larger decay time. So it's obvious that these have been designed, and these are the ones still used by nature, but now for a different purpose. That is for the storage of information. And that information, why is it stored in the DNA or RNA? It's stored it is information which is useful for dissipation in the biosphere, now at different wavelengths. But that's basically what this information is for, which is stored in the DNA, is dissipation, again, but in the visible and the ultraviolet. And now dissipation in the UVC range is being performed by the ozone and oxygen in the atmosphere. But remember, ozone and oxygen are produced by life through oxygenic photosynthesis. So these molecules, oxygen and ozone, are also life-produced pigments, if you like to look at them that way. So life is dissipating now through the whole spectrum, from the infrared and the UVC, in the long wavelength UVC range, all the way up to the red edge. So this is just to show that these two situations, this is the photonic potential of the system, is the same as the temperature gradient over the system. For a hurricane, for example, we have hot ocean surface and cold upper atmosphere that gives rise to a generalized thermodynamic potential, which is the temperature gradient over the system. And that gives rise to the formation of these structures. Well, the same thing occurs here, but with light. This is really light. Heat is also light, so temperature can be looked at as the emission and absorption of different wavelengths. So it's really the same thing which is happening, but just on a different scale and a different wavelength region. Okay, but now to get dissipative structuring, we need the precursors for the fundamental molecules. And so far, we have, for the DNA bases, for example, we need water. This should be H2O, not H3O, sorry here. And carbon dioxide and hydrogen cyanide. Okay, well, water, we know, is very common in the universe and on the planets. And so is carbon dioxide. So these molecules probably have also been dissipatively structured through light at much shorter wavelengths. But hydrogen cyanide is also very common in the universe. But now, just to give you an example of this structuring at shorter wavelengths, how is hydrogen cyanide, or how was hydrogen cyanide formed as one of the precursors for the fundamental molecules at the origin of life? Well, for example, if we have methane, which is also a very common molecule in the universe, and excited with photons of 120 nanometers, which is the Lyman alpha line. So this, you know, this is the hydrogen spectrum. So if you heat hydrogen, like in a hydrogen light bulb or on the sun, you're going to excite it into its electronic states, and it can decay from, this is the n = 2 electronic state, to the n = 1 electronic state, and that gives rise to this line, which has this wavelength, 121 nanometers. This is in angstroms, so this would be about 121 nanometers, 122 nanometers. And the same for these other, the Lyman beta and Lyman gamma lines, these, and the continuum here. This is all due to the de-excitation spectrum of excited hydrogen. So with this Lyman alpha line, and we see it here, this is in the sun, and this is on a logarithmic scale. So this here is the line, this is the spectrum of the sun in this wavelength range. This is 122 nanometers, 121 nanometers. With light from this line, we can excite a methane and cause it to leave hydrogen, 3 hydrogens, and form this excited state ion. Now this excited state ion can interact with a nitrogen molecule in the atmosphere. Nitrogen is also a very common gas in the atmosphere, so I should actually have it here. And it can form then hydrogen cyanide. Or we can go the other way around. We can excite nitrogen with this 121 nanometer line, this nitrogen molecule, form an excited nitrogen atom, which can attack CH or CH2, which could be formed from these reactions, for example. And then that going again to hydrogen cyanide. So there are a number of different ways we can produce these molecules, and we want to be able to show that the production of these molecules is also a dissipative structuring, but at these much lower wavelengths, much smaller wavelengths, shorter length wavelengths. Okay, so that's how we find these fundamental molecules. This is water, H2O, carbon dioxide, and hydrogen cyanide, and nitrogen. And from these molecules, we saw that if we have ultraviolet light, we can form adenine, starting from 4 molecules of hydrogen cyanide, and then we need 1 more molecule at the end of this reaction chain to form adenine. So there are different photochemical reactions which are occurring. Like, for instance, the absorption of a photon at 298 nanometers causes the rotation around this double bond, and that gives us to this system. And then another absorption of a photon at 313 nanometers can give rise to proton transfer from here to here. So we get this structure. And then another one causes the closure of the ring, and then chemical reactions, and then finally we get to adenine. And I mentioned that this is going over a barrier, a high energy barrier, and we can go uphill in energy. So these are the Gibbs free energies of transdam and cisdam, which are these two molecules. And we can go over the barrier. And well, there's also a probability that we go backwards. We're going to see that the probability of going backwards is less than the probability of going forwards. And we'll explain why that is in a minute. So we're absorbing at different wavelengths here. First, where there's very little light, and then finally, when we get to adenine, we're absorbing where there's a lot of light and dissipating very rapidly through this conical intersection. So we're going from a system which is not very dissipative to a system which is ever more dissipative. You could look at it, for example, in analogy, just an analogy, the hurricane going from a storm or a category 1 hurricane to a category 5 hurricane. Now, category 5 hurricane is dissipating much more of the heat gradient, of the temperature gradient of the system than a category 1 hurricane. And that's just exactly what is happening here with these molecules. So, as I mentioned, there's more probability or a higher probability of going in the forward direction. So this is looking at this interaction going from here to here. So the rotation around the double bond, which goes over a high energy barrier. And really the difference in energies, the free energies is not great, but this is a higher free energy than cisdam. Transdam has higher free energy than cisdam, but only by a little amount. This is the delta G factor. But the most important is this activation energy barrier, which the system has to go over. So at normal temperatures, it's not going to do that. You're going to have very little probability we'll get transdam. So if this system was only in a temperature bath, even at very high temperatures, there would be, most of it would be cisdam and there would be little transdam. So there's no way that we're going to get to adenine. But if we allow the absorption of ultraviolet light, then that gives us the energy, the free energy to go over the barrier in the forward direction. Of course, this molecule also absorbs, but at a different wavelength, okay, where the intensity may be different, may be greater or may be less. But we can also go backwards, back to this. So why does the system generally go forwards in this way, in this line of direction? And that you can look at as evolution on the molecular level. And why is that occurring? Well, this chemical, photochemical reaction going from cisdam to transdam is not the only photochemical reaction which could occur. As I mentioned, we can also have dissipation directly to the ground state. Okay, so this is would be the quantum efficiency, this Q, for internal conversion, okay, for cisdam. So this is the probability, given the absorption of a photon, that the system goes to the ground state by vibrational, by emitting its electronic excitation energy into heat. But there is another, the photochemical reaction, and there's many others also, which take the system to this transdam, which is the rotation around the double bond here. So that also has a quantum efficiency. So the sum of all the quantum efficiencies of all the photochemical reactions has to add up to 1. So if we give this a large value here, then that means the system would have very little chance of going to transdam, from cisdam to transdam, because all of the quantum efficiency would be going to internal conversion, which is dissipation into heat. But if it's a smaller value, then that allows us to have a bigger value for the quantum efficiency for this photochemical reaction of the rotation. So then what we need to go, because we can also go the same thing for the backward reaction. No? It's also absorbing photons and can go backwards and go back over this barrier. But if this molecule has a greater quantum efficiency for internal conversion compared to the backwards reaction, then the system will most likely go through internal conversion to the ground state. And if this is greater than this, then we're going to go more likely in the forward direction. Okay, so you can look at this here as an equation describing the criteria for the evolution from one molecule to another along this path leading to adenine. We have to satisfy this equation, which is at the bottom. So this equation represents the criteria for evolution in the forward direction. And we know, for example, adenine has a very large quantum efficiency to the ground state. So most of the absorption of photons go directly to the ground state. So there's very little photons which can allow it to go to other photochemical reactions, either backwards or forwards. So the system stays at adenine under this UVC light, continuous flow of UVC light. But also we can remove the UVC light, and because of the strong binding, covalent binding between atoms, even though the UVC light is not there, the system will take a long time going backwards because of the strong binding. So essentially that means that we get into a rather deep Gibbs free energy state here at adenine. So there's a little, with high barriers between the other configurations, so there's little probability of going backwards, although if we wait long enough and at high enough temperatures, it can go backwards. And that's why you who are studying in the laboratories know that we have to keep DNA cool, because if we don't, DNA can be destroyed by hydrolysis, for example, and go to another molecule. That's why we store DNA in the refrigerator, and that's in fact why we store all medicines, for example, also in the refrigerator. So this is really evolution at the molecular level, and explaining why it goes in the forward direction to greater dissipating systems. When you have light, UVC light, which can transform the molecule over the system. Okay, so if you like it, it's Darwin's theory at the molecular scale, molecular level. But we're not here, we're not optimizing survivability in any sense. For example, we're not optimizing the lowest energy, we're not looking for the lowest energy Gibbs free energy here, but we're optimizing stability under this UVC light. And so that, well, stability is, I shouldn't have said stability, we're really optimizing dissipation, but stability is like a, one of the characteristics of great dissipation or efficient dissipation. What we're really optimizing is dissipation. And that's what nature is doing in all of irreversible processes. So that is the dissipative structuring of the basis of DNA. But now what about the ribose, which is a sugar? Well, this is a possible explanation, but it hasn't been developed, but we would like to do that in the future. So we can polymerize formaldehyde to form ribose. Now, if you remember, I said the aldehydes are absorbing around 300 nanometers. The aldehydes are made by the photons in the UVC impinging on the different atmospheric gases. like carbon dioxide and water. So we can produce aldehyde, and formaldehyde is the easiest to produce. This is the most simplest aldehyde. And it has absorption about 300 nanometers. That's why we don't see anything here at the surface of Earth, because it's absorbing, these aldehydes, formaldehyde, are absorbing in the atmosphere. And when they absorb, they can actually polymerize. So for example, if we take 5 molecules of formaldehyde, we can form ribose, absorbing it in this range of the spectrum with a maximum of about 300 nanometers. So therefore, we can go from a single molecule to a polymer. Both left and right will be produced equally. And that gives rise to this sugar, which is ribose. Okay, this is the same, it's just in this circular form here. But we have this oxygen here, just formed a bond here instead of a bond here, double bond here, which is this double bond. So that is one way of producing ribose, through which we suspect is dissipative structuring, but we have to do all of the analysis, looking at the different absorption, different polymers of formaldehyde, and looking at their quantum efficiencies for dissipation to the ground state. So these are these Q values, the quantum efficiencies. Now, it's also been shown, this was done experimentally by Sostak in 2012, that if we have phosphate ions available in the environment under UVC light of about 260 nanometers, then we can produce, if we do that 3 times, we can produce this, what's known as phosphorylation of the nucleobases. So we assume that we have these bases formed by dissipative structuring and also the sugar. And then we have these phosphates in the environment, and we're exposing this to ultraviolet light, and that allows us to form these phosphate bonds here. So we do that 3 times and we get, so this, if this is adenine, this is adenine, so it would be adenine triphosphate. Okay, this one molecule. And so those different molecules, we do it for adenine, also for cytosine, guanine, and thymine. And then those 4 will stack one on top of the other, because they're essentially planar molecules here, and they have this van der Waals coupling between these pi bonding systems. Excuse me.
Don't worry. Are you okay?
Yeah, I'm okay. I'm just, I guess my voice is going. But, okay, so we have these. Thanks for asking, by the way. That's very kind of you. But I'm fine. So we have these different triphosphates that are these different bases, and together they can pile on one on top of each other by the pi bonding, or the really van der Waals bonding between them, and they can form these structures. And we can also have this. This gives us enough energy to form the backbone. So these can break off, and we have a connection between the phosphate of one group and the sugar of the other, and that allows us to build up these chains. And so you might say, why would the system want to go to this DNA structure? And again, we have to show that it goes to this DNA structure because we get greater dissipation when it goes to this DNA structure. First of all, what they have determined, that once we get into this DNA structure here, the bases are much more stable. So that means they have a lower reaction constant for hydrolysis, for destruction of the bases. So that would give us greater dissipation, because the bases last longer, essentially. But not only that, because once they form the structure can act as a backbone to other molecules, which I'll show, for example, tryptophan in a minute, which can be antenna molecules. So tryptophan absorbs rather strongly at 280 nanometers, but it doesn't have a dissipation to the ground state, a conical intersection. So it stays excited nanoseconds and can fluoresce. If it fluoresces, it's not very dissipated. But what it can do, it can stick to DNA and then use the conical intersection of DNA because there's an energy transfer. So that gives us another reason. Okay, and I'll go into that in a little more detail in the following slides. But that gives us a reason why the bases, in terms of this dissipation, would want to come together and form this DNA structure. Everything that happens in nature, of course, has to be through dissipation. There's no getting around it. You have to increase dissipation for structure. So that is one example. But anyway, going back to the fundamental molecules, so what we did is we looked at the absorption spectra and took the maximum. Those absorption spectra, sometimes they have two maxima. And so in case they had two maxima, we plotted the two values on the graph of the light which is coming into Earth at the origin of light. So we did that for nucleobases, cofactors, amino acids, vitamins, proteins, which are like amino acids stuck together, and pigments, and also some lipids, which are the fatty acids. And if we plot that, let me see if it shows up here on this graph, then we find that they fit very nicely around this UVC spectrum. So that gives us an indication that probably the great majority of these molecules, these fundamental molecules, are in fact dissipative structures. So as I was mentioning, we can get greater dissipation if we get tryptophan attached to DNA, because tryptophan doesn't have its own conical intersection, but DNA does. So if we imagine this is tryptophan, which is the donor molecule or the antenna molecule, it absorbs the photon and passes its energy directly to DNA, which then through the conical intersection of DNA goes to the ground state through dissipation of this light into heat. Okay, so if you look at this, this is a little bit like we're evolving the system now. And why is that? Because it turns out that tryptophan has particular binding to 3 bases, consecutive bases in a row. So it has what's called its codon. So all of the amino acids have a codon. And it turns out a lot of those amino acids, particularly the earliest amino acids, have chemical attraction to the codon on DNA or RNA. So this is a physical chemical attraction. If there was a different codon, we would have less binding. But the particular codon of tryptophan, we get strong binding, and so we get strong coupling of the light energy into the quenching molecule, which is DNA. So together, these two molecules act as a greater dissipative system. So that is why, for example, and if we now tie the denaturing of DNA to dissipation, as I did in the previous talk, you remember we have to dissipate in order to get the molecule to denature, then those molecules which have the codon, which defines or signifies tryptophan, are going to denature more frequently in a colder ocean than will DNA structures which don't have the codon for binding of tryptophan. Because to get denaturing, we need to absorb more photons. That gives us greater possibility of denaturing and therefore greater possibility of replication. So you can see how information is beginning to be stored in this replicating system. And this information is information for dissipation. Here it's very obvious that it's for dissipation of UVC light. Now, when we get to today, and we have many organisms which have different DNA, it's still the same principle which is operating. But the information in our DNA is such that we increase the dissipation, not of ourselves, but of the biosphere. Okay, so that's the same as here. It's not of the individual molecules, but of the combination of the two molecules, which gives greater dissipation. So that is another form of dissipative structuring, which is increasing the dissipation. So it's information being stored in the system, and that information has its fundamental value in the dissipation. And that is at the beginning of life and also today in terms of the biosphere or the ecosphere. And that is, of course, evolution. So that is, all of this is working on ultraviolet light in the UVC range, which we call the long wavelength UVC range. But we can also get destruction of these molecules. And that is if we have light below about 180 nanometers. So this is the ionization potential as a function of energy of the molecule. So if you put in, let's say, 7 electron volts to cytosine, you can get it to lose an electron. So you eventually start destroying the bases. So if we have photon wavelengths, so these are the wavelengths which correspond to these values of energy in electron volts. If we have wavelengths less than about 180 nanometers, which I call the medium UVC range, then we can get ionization and destruction. So it's basically the same for all the bases, more or less at about 180 nanometers and below. And we start ionizing the system and we start destroying the system. So we don't want light in this range on the surface, at least on the surface of Earth, where life is forming, because it will start destroying these bases and therefore we have no more dissipation. So then in summary, the UVC, for the different UVC dissipative processes, we have the production of hydrogen cyanide, which requires short wavelength UVC light, about 121 at the Lyman alpha line. And to produce ribose, we need this long wavelength UVC range at about 260 from this formaldehyde. And that is being produced in the atmosphere, and it rains to the surface, and then it's being used, this ribose, in forming the DNA bases, the bases with the ribose and with the phosphate. And I've also given you the photochemical dissipative structuring of adenine from 5 molecules of hydrogen cyanide. That's also based on long wavelength UVC light. Okay, and phosphorylation of the bases. It's also with long wavelength UVC light around 260 nanometers. And in a previous talk, not in this talk, but a previous talk, I gave you how we could have replication of DNA by absorbing also in this long wavelength range. So if you would like going back to this talk to find out about it, but essentially we need to absorb these photons in order to get denaturing, and that we have actually measured in the laboratory. And the denaturing using photons, of course, increases as we get towards the denaturing temperature. And at night we could have extension of pieces of segments of DNA which came together to form another double strand, in fact 2 double strands where there was initially only one.